Okay. Thanks again for inviting me. I'm really pleasure to be with you guys and share my research and some of the exciting stuff that we are doing in our lab.
Excellent.
Thank you. Thank you so much.
I'll just let y'all know I'm holding on and waiting, letting anyone to come in until you feel that you're ready. We are a little bit early here. We just have one person in the waiting room at the moment, but don't want them to see, the green room activity here. So, but I'll let you
I
know when
typically do the same thing. It's a common practice.
Hmm.
We can wait a few minutes.
Sure. How are things with you, Uttam?
Yeah, everything is fine. Everything is fine. Just busy with many things.
Yeah, this is like that time of the semester where
Yeah,
like scrambling for so many things, paper deadlines, you have
yeah,
assignments to grade.
yeah. And then we have boot camp.
I
I
see.
think in
Okay.
next month, 2 days free boot camp. 2 day free. I think it is boot camp for 2 days only for undergraduate and 2 years undergraduate program.
I see.
There also we need speaker and there will be some hands-on on
I
cybersecurity.
see.
And
I see.
thereafter during summer we have a workshop. So that is actually supported by MSCC. So there
I
will
see.
be around 25 to 30 undergraduate students. They'll be staying here in Nashville.
Oh, nice. Nice.
So 10 weeks program that is. So we'll train cybersecurity, big data, data science, and then this climate change, wildlife, wildfire. So there are many things that are happening
So is it during the semester or during the spring
during
break?
summer. During
Oh,
summer.
during summer. Okay, during summer. Okay.
So it
Awesome.
is 10 weeks program.
I see. I see. And are you going to the DoD labs this summer as well?
Still, I am waiting to hear from them,
Okay. Okay.
but only good thing is that Pushpit already got that.
I see. Okay. Nice.
Just
Nice.
yesterday she got notification,
Oh,
but
nice.
for my case, I'm not sure because
Maybe
still
it's a matter of time that you get the notification as
or
well.
may not get.
Okay. Awesome. So how much time do I have for the talk? Like, I think it's the entire thing is around 1 hour, so maybe around 45, 50 minutes.
Yes, and then there will be question answer. So
Okay.
first, I'll introduce our cybersecurity initiative, and then Professor Sajid Hussain, he will introduce you,
Okay.
and next there will be question answer session.
Okay. Sure. I mean, I
And
think I have too many slides. So since this slides deck is like completely new,
mhm,
a kind of culmination of what I did for the last couple of years. So I
yeah,
have maybe around 80 slides, but again, based on how much time I have, I'll probably
yeah,
skip.
you can get 50 minutes to 55
Yeah.
minutes, and
Okay.
then there will be question answer.
Sure. Sounds good. And yeah, let me know. I mean, if I am like maybe when we have like 10 minutes left or something, just give me a quick.
Yeah, yeah, sure.
Yeah.
Are we ready to start letting in our guest?
I think so, yeah.
Okay, all right, here they come.
I think it's 12 o'clock. Okay.
Okay, let us start. Good afternoon, everyone. My name is Uttam Ghosh. I am working here at Associate Professor of Cybersecurity in the Department of Computer Science and Data Science, Meher Medical College. And I would like to welcome everyone for our Mehari Cybersecurity Initiative. So in this initiative, we are organizing uh, seminar series and as well as workshops, summer workshops, and also we are doing a lot of activity related to cybersecurity and data science. And this initiative started by our Dean Fortune. And this initiative actually, our director is Professor Sajid Hussain. He is professor as well as department chair, and also he is the director of this cybersecurity initiatives. And today we have a guest speaker, Dr. Saptarshi Debroy. He is from City University of New York. He is working as associate professor, and I would like to Professor Sajid Hussain so that he can formally introduce our guest speaker. Yeah, thank you, Professor Sajid Hussain. Please introduce.
Thank you, Dr. Ghosh. Really, it's my pleasure to introduce our speaker, Dr. Debroy, in this our seminar series regarding our cybersecurity. So, Dr. Debroy is an associate professor of computer science at Hunter. Okay. So Dr. Debroy is an associate professor of computer science at Hunter College and a member of the doctoral faculties at the Graduate Center of the City University of New York. He received his PhD from the University of Central Florida in 2014. Before joining academia, he worked as a research scientist at Motorola and Blue Coat Systems. His current research interests are in reliable and secure edge AI. He has published more than 50 papers in top-tier peer-reviewed journal and conference proceedings. He has experience managing multiple research and educational projects funded by federal agencies such as NSF and DOE and other even private corporations like Google and Verizon. His accomplishments include the NSF Early Career Award, a nomination for the Presidential Early Career Awards for scientists and engineers, Best Paper Awards, and a university gold medal. He is a senior member of ACM and IEEE. His credentials really prove that he's a top researcher, well qualified, and we are fortunate to have him for this seminar series. So please help me welcome Dr. Debroy.
Thank you, Professor Hussain, for the kind words, and thanks, Professor Ghosh, for inviting me and giving me this opportunity to talk about my research. Hello, fellow listeners. I am Saptarshi Debroy, and I am Associate Professor and Doctoral Faculty at City University of New York. I am the founder and director of Distributed Systems and Security Lab. So without any further ado, let's start with today's proceedings. So this is the outline of the talk. First, we'll talk about a little bit about the lab, what we do, what is our expertise, and some of the kind of projects or like overarching themes that we do in our lab. Then we specifically talk about one problem. So this is kind of a culmination and a summary of what we did for the last couple of years. I think most of the projects that we're going to discuss today is about things that we did in the last couple of years. So we'll start with an application, and then which is specifically just-in-time edge environment, and then go into the vulnerabilities that we explore, and maybe touch upon some of the solutions that we proposed in some of our recent work. So we start with the Dissect Lab, which is the lab that we have. I'm the founder and director. So I would call myself and the lab, the focus of the lab under the Louis Pasteur quadrant of research. So our research is mostly use-inspired basic research. So we find a use case and we find the system design challenges. That's why our lab is called Distributed Systems and Security Lab. So we solve system design challenges, system management challenges, as well as security problems. But everything stems from some use case, some real application. What are the problems with that real application? How can we cater to that application? So that's why we say like Dissect Lab, we are solidly within the Louis Pasteur quadrant of research. Most of our research is science driven, as we talked about it, innovative. I think all research is innovative in that way. Collaborative and interdisciplinary, and we'll show like how much we collaborated with other people within CUNY and outside CUNY. It is leveraged because it builds on some existing research, strategic in terms of importance and how the strategic vision of the country and research aligns with our research. Engaging in terms of engaging graduate student, undergraduate student, PhD students, and also high school students in some cases, and sustain so that the outcome of research sustains the duration or kind of extends the duration of the research period. So this is kind of big picture Venn diagram of what we do. So we have distributed computing, which I think is kind of a bread and butter of what we do. And then there is also big data as the application, whereas data science is the tool which we kind of cater to. And then there is security and privacy, in terms of vulnerabilities and existing threats or new threats that can be explored. So this is kind of the big picture Venn diagram. And some of the examples which kind of fall within the intersections are like solving resource management problems, which are the systems part of distributed computing. The solutions are mostly data science driven. Then synthesizing reliable by design solution, which is in the intersection of data science and security and privacy. And then if you are only talking about security and privacy of distributed systems, then the research we do is kind of exploring new vulnerabilities and threats that exist or persist in these futuristic distributed systems. So an overview of the kind of capabilities that we have in the lab. So we have like a multi-tier test bed setup. So we have a device plane where we have some Kinect cameras. We don't have it right now, but we have the data from the Kinect cameras. We're in the process of buying more. We have some smartphones that act as IoT devices. In the wireless planes, we have some USRP devices which can be programmed to act as a Wi-Fi access point or an LTE base station. Then we have on-premise edge devices where you have like very small devices like Jetson TX2 or Jetson Nano, which has some GPU capability, but not that much. And then network edge plane, we have some powerful Dell PowerEdge servers. And then we have internet connectivity to Fabric, which kind of acts as our cloud plane. We kind of offload most computationally intensive work to the cloud plane. Some impacts and highlights. I've been working in industry and academia for last 10 years in different capacities. I've managed federal and industry grants. In terms of publication, personally, I have more than 50 publications. In the lab, we have more than 30 publications. The journal conference venues are pretty top-notch, so that's what we target. And in terms of recognition, I've been awarded Career Award, and then I was nominated with the PCASE Award. Recently, I've got Google Research Award and some Best Paper Awards. So this is what we mean by collaboration, and this is a common themes are distributed systems, security and privacy, smart applications. So they kind of generate proposals, and hopefully the proposals then generate papers as well. Knowledge impacts like collaboration creates new research direction, education direction, and hopefully money to sustain the lab and to write quality publications. These are some, again, I could have put some names, but I think it's faces that matters more than the names. So these are like four main thrusts of the research we do. And you can see that one of your own, Uttam Ghosh, he actually features in the midst of the faces. And these are some of the institutions that I'm collaborating. Sorry, was there a question? Okay. And again, these are the superstars of the lab. So before we start, we have to mention my students. So I say I'm the face of the operation, and but these are the brains of the operation. So they are superstars in their own right. We have some current students. We have 6 PhD students, and we have some prior members. And they graduated in 2023. One student is in academia. One student is in industry, and I have many undergrads who I work with. And then thanks to the sponsors, goes without saying, NSF has been the biggest sponsor of most of my research. Recently, I got a grant from Google, and then my first grant was from Verizon Foundation, and City University and Hunter College has always been funding my endeavors. Okay, now we come to the first part, the technical part of the talk, and we start with just-in-time edge application. So we start with the motivation. We have been working with Fire Department of New York. So this is their vision of a fire rescue in New York City. So you have a fire scenario, maybe a high-rise building or somewhere. So before you send out the first responders, you send out drones or robots, which will collect live streams from those scenes using some Verizon infrastructure. They will be offloaded to Amazon Web Services for fast computation, and then the result or the computed data will come through those infrastructure to the ground first responders It can be more for medical triage. It can be for rescue operation. It can be for even tactical scenarios. So the applications are many. But the common theme is most of these applications are mission critical. They have real-time requirements, and most of these are data-intensive AI applications, which I think it's very common these days. So, so the question is, how do we do this? So, because again, in this case, we are mainly solving the computation problem. So, where to do the computation? So, one option is to do the computation at IoT devices, which the good thing is it will give you ultra low latency because the devices are right where the ground responders are, who are going to be the consumer of the data. But the problem is this is constrained devices, too unreliable. Devices go up and down. They don't have energy, so it's very unreliable. The other option is doing at network edge. So you have infrastructure, and that's where you do it. It's low latency, but you have to depend on infrastructure. What happens in a disaster scenario? Infrastructure is gone. What do you do then? And then these agencies, they have to spend a lot of money to get these things done. And like any state and federal agencies, they don't have a lot of money. So the other option is cloud. Okay, if you do things in bulk in the cloud, maybe you get some discount. The problem is it is too far, right? The computation can be quick. You can buy a lot of resources, or you can rent a lot of resources rather, but it's too far. In some cases, it's privacy violation. You are not allowed to send everything to the cloud resources. So what is the alternative? What we propose, or actually it's not us, but we were maybe the first few people to propose it, but again, it's kind of catching up, which is how to provide reliable near cloud scale resources for mission critical real-time application on premise. So that is the key. How can we provide this closer to where the data is collected and the data is consumed? So what we propose is something called just-in-time edge resources, or on-premise resources. So an example can be a multi-utility vehicle having computation devices, and it has some like infrastructure, the network infrastructure. So you generate the data from the devices, you send it to the nearby edge server, not something hosted by the net like service provider, but something which is hosted by the agencies themselves, and get the computation done there. And the realities of such a system is that the applications are completely heterogeneous. You have algorithms which sometimes are batch processing, sometimes they are neural network based, and these days I think mostly neural network based. The data type can be unimodal, multimodal, different types of quality of service requirements. Some are high on delay, some are high on energy conservation, whereas in some cases accuracy is the most important thing. And the environment is changing all the time, especially in maybe a tactical scenario or a disaster scenario where these just-in-time edge environments are most applicable. And yeah, you have different types of heterogeneous devices. So let's talk about some of the applications. Again, it can go from very simple applications such as object detection, object classification, pose detection, face detection. I mean, there's a vast sway of applications. And these days we are seeing people are talking about LLMs. I mean, till I don't think I have found an application of LLM for these kind of scenarios, but people are at least starting about it. So the point is most of these applications are deep neural network based. So these are data intensive and compute intensive. And if you want to perform them, if you want to do this computation in IoT devices, that's a disaster because they simply do not have the capacity. So what is the other option? The other option is, okay, let's offload everything to the just-in-time edge resources, or to these multi-utility vehicle hosted computation places, right? So there are many problems with that actually. First problem is these devices are also constrained. I mean, they have more capacity than IoT devices, but they are not unlimited capacity. They are no way close to cloud scale capacity. So first is if you offload everything, you end up creating a bottleneck at these edge servers. So that's one problem. The another problem, which is a little counterintuitive, is sometimes offloading everything to these edge resources is counterproductive. So here we kind of, in one of our earlier papers, we did some experiment where we showed that, let me use my laser pointer. We showed that the amount of data that you are transmitting, if you are offloading everything, is much higher than amount of data you are offloading if you do some computation locally. So you see in application 1, we are doing some computation locally and we are sending the rest of it to the edge server. Whereas in application 6, we are sending the entire data to the edge server. So we see that if you do the entirety of it, and if you do some intermediate data, obviously the data size, the amount of data you are transmitting is going to be much less. So you are saving on energy in terms of transmission energy, you are saving in terms of transmission latency. Whereas this is not true for all deep neural networks. It works for some deep neural networks. We have to be intelligent about it. So the point is that, okay, we are achieving some energy savings from offloading the tasks or DNN computation from the device to the server. But then because we are sending the entirety of the data, that it's taking its toll in terms of some energy cost and some computation and some transmission time as well. So sometimes transmission cost of task offloading outweighs the energy preservation benefits. So it's not really ideal. So what we proposed is something called DNN partial offloading, and this is now kind of a very well received concept in the community, where you do some computation. So if you have a DNN, you have multiple layers, you do some layers locally and then offload the rest of the layers to the edge server. So you are not doing the entirety of the DNN computation locally at the devices, or you are not doing the entire thing remotely at the edge server. So this is called DNN partial offloading or DNN partitioning. So this is how the concept goes. You have a deep neural network. Here we are showing like a convolutional neural network, which is mostly used for computer vision applications. So you cut it somewhere. Okay, cut means these are the layers which are going to run by the IoT device or small device, energy constrained device that you have, which is collecting the data. And then the rest of the layers, hopefully a lot of those, you are going to run remotely at the edge servers. Now, the challenge, the scientific problem that we face here is how to find the optimal cut point, where to cut, right? Again, it can depend on different DNNs. You have like within even computer vision DNNs, different DNNs have different characteristics. And then if you go beyond that, beyond computer vision, maybe LLMs, the problem becomes even more challenging. Which is optimal partition, where to cut, which can balance between energy consumption and latency. So these are the two kind of metrics that we are trying to optimize. So here we kind of show how the cut point can change based on system factors. So I would like to draw your attention to these like 4 circles here. These stars mean based on measurements, this seems to be the optimal location, right? So this is AlexNet, and these are different convolution layers. And if you have a very limited uplink data rate, because you are here, uplink is what matters because you are trying to upload the data from the devices to the edge server. So if you cut it at layer number 8 for AlexNet, while the upload rate is 8 megabits per second, say something around like LTE, this is something near LTE upload speed that you will get, it seems that layer 8 is the optimal layer where you should cut. Now, if you have a higher upload rate, say 20 Mbps, something like a Wi-Fi upload speed that you get, maybe in 2.5 gigahertz, in 5 gigahertz, you are these days getting much more than that. The upload, the optimal cut point seems to be layer number 3. Okay, so based on environmental conditions, where do you make the cut might change. So these are in terms of latency. If you want to optimize latency, what if you want to optimize energy consumption? Because you're trying to optimize energy consumption of the devices and like all the devices together. In that case, if the data rate is lower, optimal is 3, which is very similar to when you want to optimize for latency, but for higher data rate. But if the data rate is higher and if you're trying to optimize energy consumption, maybe the best cut point is 1. So you cut it in the first convolution layer, you do the first, like if you do no layers locally and do all the layers remotely. And you see, this is only for AlexNet. If you do other DNN models like ResNet or VGG, this cut point identity might change. So it can change based on different systems factors, right? So this was only based on energy and latency. Energy is the device energy that we are trying to preserve, because these devices are essential for the operation of the application. And the latency is because you want to make it real time, right? What if we bring in another challenge, another metric to optimize, which is accuracy? Because for DNN applications, maybe you're optimizing between energy and latency, which is impacting your accuracy. Because if you're running these AI applications, you want those applications, you want those DNN models to be accurate in terms of whatever they're doing. If they're doing detection, if they're doing classification, you want the high accuracy, right? So if you want to like do this three-way optimization, it's even more challenging, right? Because you have different models, and here we are not comparing like completely different models. Say you have VGG, you have two different models of VGG 19 and 11. Again, there are VGG 16 based on how many convolution layer it has. The accuracy might change. Same data set, right? The latency is changing, which kind of established the amount of energy it takes from the device, kind of established that. Even the accuracy is changing. Between two versions of DenseNet, accuracy changes. Between two versions of ResNet, accuracy changes, right? So now we have a three-way kind of a optimization problem. And I think for just-in-time edge environment, these environments, all of these three are equally important, right? So how to do that? So it's a challenging problem. So this is kind of for DNN partitioning, what we do in one of our problems or one of our papers, recent papers, which is getting published in NORMS 2025, where we kind of optimize it as a, or kind of formulate it as a three-way optimization problem, which is actually a mixed integer nonlinear programming problem. And there are many ways to solve it. You can use like a heuristics method, kind of a white box approach. You can do it using a reinforcement learning method, kind of black box approach, where you do not have any idea about how how the benchmarking is. And that's what we're going to solve in this paper that is going to be published soon. So so as an optimization problem, what it is solving for DNN partition. That means where to do the cut, which layer where I make the cut. It also do in a multi-server, multi-device setting, it will choose a server. It will also dictate how much networking resources you're using, how much computation resources you're using from these devices and also from the server. And at the same time, because it is giving so much fine-grained information, it also requires some information from the system itself. Like it's kind of a monitoring and reporting kind of an environment, because you want the device resource status, because otherwise how do you know what is the computation capacity, how much leftover capacity it has, right? So you need device resource status to be periodically sent to whoever is optimizing it. You need network status to be monitored and reported. You need server resource status to be measured and reported. So these are some of the requirements, right? So here I will take a switch, right? I'll kind of switch gears, because so far I just wanted to explain you what the problem is, or what is the scientific kind of innovation that is required for just-in-time edge environment. Now we'll go and explore some of the security and privacy issues that pertains to this kind of a problem. So let's talk about the vulnerabilities. So what are the soft spots? So again, kind of reiterating what applications such as this would look like. Your video surveillance site, you have these cameras maybe kind of surveilling the scenario, and you have these edge servers which are hosted by these multi-utility vehicles in a just-in-time edge native DNN partition. So here you have like images or video streams getting collected by the drones. They are being forwarded to the edge servers. Maybe you because it's DNN partition, you are doing something locally and then sending the offloaded data to the servers. But while you are doing that, you also have to report the resource status, right? You have to report, these drones have to report exactly how much energy do they have, exactly how much computation capacity they have. So maybe they have some drivers which can run these executable files inside these devices, and then figure out how much is left, and periodically reports that to the edge servers or to the optimizer which is taking this decision, right? And then finally, these edge servers or maybe the optimizer, wherever it is, it dictates, okay, for the next few image sets, drone number one, you run the first 2 layers, drone number two, you run the first 3 layers, and drone number three, you do not run any layers, offload everything to the edge servers. That is the kind of the ecosystem that just-in-time edge environment kind of dictates, right? The problem is that this environment is fraught with challenges, fraught with potential soft spots, because this is a very loosely coupled system. So again, this is not a tailor-made system by any stretch of imagination. This is like an ad hoc kind of a system. You have a scenario, you build a system that operates for something around 2 hours to 72 hours, and then you dismantle it and you take it off, right? So this is just like a ad hoc a system made in an ad hoc manner and serves a specific purpose. So it's loosely coupled. They are not, the devices are completely heterogeneous. They are by different manufacturers, and you just like it's kind of a makeshift environment which has a specific purpose. And that's why you can have like attacks which can target the devices. And there are many ways of attacking. I mean, there are loads and loads of research which talks about like data injection, data leakage because of malware issues, because of faulty software, because of Trojan or supply chain problems. So a lot of research has been done in this space, which shows that in these kind of environments, the network and these small devices are very vulnerable and may lead to data leakage and false data injection. So, so most vulnerabilities kind of target data at rest and data in motion. So data at rest is where the data is residing currently. So if you are targeting the drones, that would be kind of data at rest. And if you're targeting the network where the data is flowing from one place to another, that would be an example of data in motion, right? And in most cases, these impact the operation of the system or the application itself. In this case, the application being some AI or ML application. So in this today's talk, we are going to kind of focus on problems where the vulnerabilities exist in data in motion, and it is impacting both the system and the application. So first we talk about system vulnerability. So kind of recalling what DNN partitioning is all about in just-in-time edge. So DNN partitioning requires these information. It requires device resource status, it requires network status, it requires server resource status, periodically sent to the optimizer, right? And therein lies the problem. The problem is, what if this data is falsified to gain unfair advantage or just to botch the system operation, right? So you have selfish and malicious different kind of scenarios. So many ways of doing it: intercepting data in transit. Here, the data in transit, the data is compute information, energy information, network information. And there are many well-known vulnerabilities like leakage through network, leakage through intermediate devices. If you're using some relay nodes or something, many techniques to do that: eavesdropping, hijacking, man in the middle. The focus of this research or our research is not how to do the interception, because there has been enormous amount of research that has happened. What we are trying to understand is what are the implications of these attacks or of these data falsification on system performance. So that's what we are trying to explore. So here we kind of do an ontology. This is one of the first few works which kind of got published in SEC Symposium on Edge Computing workshop. Or we're going to take like a deeper look at how kind of these attacks kind of evolve, right? So mainly data falsification in these kind of systems can be malicious and or selfish, right? So under selfish, especially if you are only doing dealing with energy information, because again, there are many information that is going from these devices to the edge servers. But let's say we are only dealing with energy information. So if you are if this the point of falsification or the falsification entity is energy information. So what can a selfish attack gain? So it can either be saving own energy or maybe draining others, right? So these are the two types of attacks or goals that we can think of. And both are additive in nature. Additive means that what is actually your energy expenditure, you are misreporting it, you are falsifying it by reporting more than what you are actually consuming, right, or actually expending. So here this value, this I, which is a function of zeta and delta average. So zeta is kind of the scale of attack, which dictates how many devices you are adding this information, and delta average is your exactly how much you're adding. Together it creates the intensity of the attack. So this is the value that you're adding to your original expenditure, and this is what you're reporting, right? So that's why we call it additive attack. Then you have a malicious, which malicious can be just cause operational damage. You just want to botch the system, right? So that would be an example where you are doing deductive attack, because what you want is you want to misreport, but less than what you are actually spending. So again, this is the intensity of attack function of zeta and delta average. And again, how zeta is calculated, how the delta average is calculated, that is the purpose of research. So in this particular paper, we take kind of an experimental view, data-driven view. We run a different kinds of experiment, different kinds of data. We see what the data characteristic is like, and based on that, try to find out what is the optimal delta average if you want to achieve this level of success in terms of attack. And again, the point is you want to evade anomaly detection, because you do not want to do a brute force attack, because that kind of it's not stealthy, and it's very specific. It's not a DDoS that we are looking for. It's more of a stealthy attack. So you are trying to undermine the system, but yet evading detection. So these are some of the very early results. Again, most of these results are collected through the experimental setup that we have, which we already talked about in the DISEC lab. So we use some part of that ecosystem for some papers, some experiments. So here we show, like, the first set of results are saving own energy. So that is the attack that we're talking about. Here you are reporting a little bit more than what you are actually spending in terms of energy. And we can see that all the devices, right? So this is what we're calculating break-even time. Break-even time is from the time we are starting the attack, and from the time till the time when the attack succeeds. In this case, the attack succeed is that while the work is distributed, because again, the work is how many layers we are going to run, right? Because that will dictate how much energy is being consumed by these devices, because everybody is doing some or computing some layers. So here we see that within, say, 1500 iterations, here we are doing in terms of or rather 20, 30, 25 iterations we are doing in terms of iterations, because absolute time will be depend on other things, because it will be dictated based on in what frequency these devices are sending this information. And we felt like those are much more specific values and depends on different systems. So we are doing this in terms of number of iterations. Again, exactly iteration to time is just multiply this value with some like the time for each iteration, right? So here we see that for different values of delta average, we have different number of iterations till the attack succeeds. And similarly, if you want to do it for like another selfish attack, which is drainage of others' battery, because in this case you have to report a little more than what actually is happening. Here you are doing, you're adding some value, but you're adding more value. Why? Because if you are only trying to save your own energy, what you do is you misreport a little more, that okay, I spend 2 joules, I'm saying I spend 2.5 joules. So now the optimizer will ask me to do less, right? And that will save my energy. Whereas if you want to drain others, because there are other devices in the system, you want to drain all of them or maybe some of them, you have to misreport a little more. So you are spending 2 joules, you are saying I spent 3 joules instead of 2.5, so that everybody else is pulling your share, because you are spending more, everybody else now, I mean, for the optimizer, you are spending more. So in the next time, the optimizer will say, okay, you do less, the others will pull your share, and that will be the vehicle through which you end up draining others. So that's kind of some of the results that we got from this this paper. Now we'll switch gears to application vulnerability. So this example was how the system can be impacted, how you can drain a device, how you can save your own energy, how you can cause operational damage, like maybe jeopardizing device safety and security, right? So that's what this attack was all about, falsifying data about the system. But now we take a look at falsifying the data, other type of data, which can impact the application. And the first attack or first example we'll see is model extraction. So imagine you have a deep neural network model, and there is some adversary who can intercept the cut point information and the intermediate data, because again, for DNN partitioning, that is paramount, because where the cut point is may change based on DNN. It may change based on what is the environmental condition, data rate, how much energy is a device have, how much computation a device has. So this cut point can change. So now the devices has to relay that information that, okay, I am cutting at layer number 3. So the server has to run from layer 3 to layer n. So that cut point information has to be sent from the device to the server. And also the intermediate data, because you cut it somewhere. Again, keep in mind, these are all happening during DNN inference, not during training. Imagine the training is already being done, right? So you cut it at a layer, and then it generates some intermediate data, which the server will use to run the rest of the layers. So this information needs to be sent from the device to the server, and therein lies the vulnerability. So the question is, can an adversary intercept that data to recreate the model? Again, there can be many reasons for recreating the model, because model is something which is like a private information, because in a application such as this, nobody wants to let a third party know that what model is being run for some application. So here the adversary is trying to extract the model, which kind of is a violation of confidentiality of the DNN model. So here we are adopting an autoencoder, which is creating a shadow model. And so the idea is you'll get the intermediate data, you generate like a encoder and decoder. So the decoder is trying to decode or mimic the layers in the actual original model till the cut point layer. So that's what an autoencoder does. So you generate the original input. Again, you don't have the original input. There's a completely black box attack. So the attacker does not have the original input. So what the attacker is trying to do is create or recreate the original input, and from that recreating the intermediate output, which has got its hands too. So it requires training. So hopefully this cut point layer will change at different times, and the attacker can get access to the cut point layer and cut point layer information and the intermediate data, and it keeps on training, and hopefully after a while it will be able to recreate the layer, recreate the model And here we assume that the attacker has a zoo of possible victim model, because if the attacker knows that it is an object detection or object classification kind of application running, then there can be these 30 different models potentially which the application is running. So it has this zoo, and based on the outcome of the autoencoder training, at some point it will say, okay, I have enough training done, so now let me compare my model with the zoo, and whichever matches well with the zoo of models, that particular model is the model in question. So it's completely black box and query free. The attacker does not have access to the input data or the training data set, and is trying to figure out what the model is. So here we show some examples of that. So here we can very small, because I mean, I don't want to spend a lot of time on this.
Andy,
Yes. Hello? Was there a question? Okay. So here we are seeing that here the original model is VGG16, and you see that this is the dark purple, and VG16 is the best similarity with the model zoo. This is the model zoo, the potential models that you have. So in this case, our attack was successfully able to identify that the original model is VG16. Here, the original model was ResNet 50. Our attack was able to successfully identify that it is ResNet 50, and then for mobile net, it's mobile net. But important thing to observe here is, which I want to focus, that it is not the success is not guaranteed for all DNNs, right? So that is the important thing, because for VG16, you see VG16 and 19 very close similarity. It's a little bit higher, but still it's kind of a touch and go. Whereas ResNet clearly the most optimal model, or rather the clearly the model that the attacker is trying to extract. MobileNet, clearly the model the attacker is trying to extract. Not for VGG probably. So again, certain DNNs are more vulnerable to such attacks, certain DNNs are not. So this is kind of a unique finding that we could find, and this kind of getting published in norms as well this year. So then we'll talk about another application vulnerability, where the first one was model extraction, which is kind of a confidentiality violation. Here we are talking about integrity violation, because we want to change the outcome of the model. So that's what we are trying to do. Again, same scenario, just-in-time edge, DNN partition, because that's what we are trying to understand the vulnerability of, right? So in this case, the idea is that the attacker has the same inputs, which is the cut point information and intermediate output. Can it use it to add just enough noise to the input data so that the outcome of the original model will change, the classification will change? So again, the focus is not how to intercept, but on what are the implications of if you can intercept, right? So before we go to in the results or the process, here we are showing the motivation, why it is an important or a non-trivial problem to solve. So these are two different models. I think these are DNN and AlexNet, and these are the classifications based on different layer outcomes. So the point is, if you get an intermediate input, it doesn't mean anything, because it's in the middle of getting processed. So it's like you have a image of a bus, and you are running a VGG on it to figure out it is a bus. If you cut it at the convolution layer 3, whatever you get, it's very difficult to figure out what it is. So this is what we're trying to say. Like, if you use it for classification, it will not mean anything. So all these classifications are kind of jumbled up. There is no clear clustering where you can say, okay, a bus, a image of a bus after layer 3 is distinctly different from image of a rat or a dog after layer 3. These are completely kind of not understandable kind of images which cannot be used for classification. So it's very non-trivial for an attacker to get this information and figure out what that information means. So in this case, we are kind of training a variational autoencoder where there's an encoder and decoder part. So the point is, so you have some information from these intermediate input or rather intermediate output. So you perturb it to get the latent features, feed that to the decoder of the variational autoencoder and generate some samples which can significantly deviate from the original input. Again, this is again black box and query free. So the attacker has no knowledge about the model, what model is being used. It has no knowledge about the input data. It has no knowledge about the training data set. So the only tool it has is the variational autoencoder, which is a combination of encoder and decoder, and is getting the cut point layer information and the intermediate output, and then adding enough noise to it so that it changes when you run the rest of the layers of the original DNN. So that's the entire point. And this is not yet published. So these results are from a paper which is currently under submission. So this is kind of a qualitative analysis of what we do. So if you have no attack, these will be the pictures like visually, and these will be the certainty or the confidence of the DNN model. I think it's for VGG on these categories, on these classifications. If you have very low intensity attack, we see that we can add enough noise so that this orchid becomes rose and the lizard becomes snake, right? And you have like the images changing visually. And then if you have a high intensity attack, we can completely change these images. Again, keep in mind, these are machines which are trying to figure it out, not a human being. And the important thing to measure or to see here is high certainty. So we are not only changing the classification, we are also changing the classification high certainty. So DNA is very certain that this is a picture of orange. Originally, it was an elephant. This is a rocket. Originally, it was a bridge. And this is a skyscraper. Originally, it was an orchid. So that's what we are trying to get to, right? And again, another interesting find is not all DNNs are equally susceptible or vulnerable to these attacks. For AlexNet, you see that even like low intensity, the accuracy is somewhere moderate. High intensity accuracy is very low, similar to VGG. But for MobileNet, even at a very low intensity, the accuracy is changing. So here, any perturbation will let the system know that there is something wrong, because what you want is high accuracy, right? Or high certainty of classification. A little bit of change means it's something wrong somewhere. So MobileNet is in a way, the way it is designed, if you do certain changes in the intermediate data, the system falls apart. So the system will say, okay, the system can say, hey, it's something wrong with the system. The MobileNet is not behaving properly. Something has gone wrong. So not all DNNs are equally susceptible. That's the point that we are trying to make. So here we are showing another example of like attack success rate for VGG and AlexNet. You see the success rate depends on the attack strength and also the layer. So if you make the cut point layer at 3, right, attack success is high. If it is 6, is low. So attack success strength at like lower strength, I think layer 3 is where you want to. I mean, layer 3 is more vulnerable. Whereas if the attack intensity high, layer 10 is more vulnerable. So certain DNNs and certain partitions in terms of certain layers are more vulnerable to such attacks, which is a very interesting find that we got in our paper. So now we switch gears again. So we talked about these problems. Now let's talk about like a probable solution. So another recall of, again, because I'm making this recall so that I make sure that we are all on the same page in terms of what DNN partition at just-in-time edge means. So this is again, many vulnerabilities exist. We saw some vulnerabilities about system, some about application. So you can either solve them one by one, or you can come up with a resilient or a reliable system, right? And keeping in mind this just-in-time edge, this is not a system which will be implemented for posterity. No, it is a system which you build, you run it for maybe 2-3 hours to 2-3 days, and that's it, you are done. So maybe it's a better strategy to make it reliable by design rather than solving or finding all different possible problems and all different possible solutions. So that's the approach we are taking. And again, there's another area of research on anomaly detection. How do you detect whether there's some problem has happened. So if you have a system vulnerability which kind of being exploited, if you have an application vulnerability which is being exploited, so there is a different area of research. We are not really currently focused on that. We are more focused on how to recover, how to build a system which is reliable by design, where these kind of problems will not overall matter to what the objective of the system is. So to do that, we'll talk a little bit about a completely different area, which is portfolio theory. Okay, and again, I'll hope, trust me, will show how this is relevant to what we are talking about. So portfolio theory is an area of research in stocks where the idea is, and I think most of us who have any knowledge about stocks know that it's better to have a varied portfolio. It's better to have a diversified portfolio, because a particular stock here, Microsoft, over during a day, right, it can fluctuate, right? It can fluctuate from 1% to say 3%, right? So this fluctuation is relevant for any stock. So this is an example of say a stock like McDonald's. So McDonald's, in terms of a standard deviation and expected return is how much you can get out of that stock, and standard deviation is how much it fluctuates, right? Again, it can be in long-term horizon, it can be short-term horizon. So imagine McDonald's is here, right? And then Bristol Myers Squibb, which is I think a healthcare stock, kind of the company has been forever. The return is not exceptional, but again, does not fluctuate a lot. It's not that volatile. So this is somewhere here, right? So the idea is have a diversified portfolio. Imagine you have 45% McDonald's and 55% Bristol Myers Squibb. This is where you want to be. So this is where your expected return is not super great, but your volatility is also much less. So this is like the fundamental of portfolio theory, that expected returns and standard deviation vary given different weighted combination of the stock. So instead of having one stock, have different stocks, but not all from the same category. So don't have all tech stocks. Have some tech stocks, some healthcare stocks, some other kind of stocks groceries kind of stocks. Have a diversified portfolio. That's what it says. So the Markowitz diversification talks about non-random diversification. So don't just randomly choose stocks. Have a careful choice of balanced portfolio. You do active measurements, like figure out how much is the expected return, how much is the variation in terms of standard deviation. And then the main part is investigate relationship between stocks. Like if you have a stock, say McDonald's and Bristol Myers Squibb, if McDonald's goes down, Bristol Myers Squibb goes down as well, that's a bad investment. You want to have a scenario where if McDonald's goes down, Bristol Myers Squibb goes up, so that we have a balanced expected return. That's what you should go for, rather than having all tech stocks or all healthcare stocks which go up and down together. So that's what you do not want. Again, another switch, and this is the way that it is designed, because without this, I think this is the best way to explain what we're trying to do. Is so keep in mind what we talked about portfolio. It will be relevant very soon. Now let's have a switch to 3D reconstruction. So far we talked about like simple AI applications. Now we're going to talk about more complex AI applications, say 3D reconstruction. Why? We'll understand very soon. So 3D reconstruction or multi-view 3D reconstruction is you have a 2D, 3D object captured from 2D cameras from different viewpoints, fused together to get a 3D visualization. Very relevant for a lot of healthcare triage applications, very relevant for a lot of tactical scenarios, disaster response, public safety, 3D reconstruction of an outdoor and indoor scene. Typically, this is how you do it. You do a multiple view geometry, same scene, same time instance from different angles, fuse together, create a sparse point cloud, create a dense points cloud from that, create a mesh, texture the mesh, and get a 3D visualization. So these are typical, most of the algorithms kind of follow the same strategy. The point is very difficult to do these things in a just-in-time edge. It's easier to do object detection, classification, recognition, 3D reconstruction, multi-view, where you have streams of videos coming in and you have to do reconstruction at every time instance. Very difficult to perform. One way to, like, because what you're trying to do is trying to do this in real time or close to real time, because these are multiple video streams, most cases high quality, fuse all of them together through an AI application, which itself takes a lot of time, is kind of a recipe for disaster. So there is a different school of work, including this paper that got published a couple of years back in SEC, which talks about how can we do it in a more efficient manner. But that is not what we're trying to say here. What trying to do is what are the vulnerabilities of these systems, or how can we make it reliable? So this is kind of a lab setup that we have, multiple cameras. We are collecting the scene. These are the different viewpoints of the same scene at same time instant. And then you have different types of activities. You have pickup, which is low dynamism, walk, high dynamism, handshake, very high dynamism, like collected together from different places and creating this kind of 3D outcome. So that's what we are doing. The point is, how can we do it in a real-time manner or close to real-time manner? Maybe we can reduce the resolution, maybe we can get rid of some cameras, but then that brings down the quality of 3D reconstruction. So again, very, very, very relevant to what we talked about before. Most AI applications have an inherent latency, energy, quality problem. What we are trying to establish here is 3D reconstruction, although it is very different from what we talked about, also had this latency quality problem or accuracy problem. Accuracy quality are kind of same thing in this case. Here we are not really bringing energy, but you can bring energy and make the problem even more challenging, right? So now we want to make this reliable. That's the point. We want to make this reliable. Imagine in a scenario where you have cameras going down, devices, energy is being drained. So you don't have data coming from one device. Your network goes out, so the data is not going from the cameras to the edge servers. What happens then? So these are disruptions, right? These are problems that can happen, which are effect of all these attacks that we talked about. System attacks, kind of a disruption. Model extraction attack, disruption. Somebody knows what the system is, what the application is, and tries to do something about it. Then classification, so 3D reconstruction, but like the outcome is being altered. So these are different disruptions, right? How do you deal with this disruption? And here we'll kind of tie this with the portfolio theory. So we are recalling the portfolio theory kind of principles and fundamentals and bringing them here in just-in-time edge resource. So a probability of stock fluctuation, what is it? For our system, it is probability of resource getting disrupted for many reasons. Again, what the reason is not important. Hopefully we have some anomaly detection which tell us that this system is disrupted, because again, in this research, we are not really working on the anomaly detection part. Standard deviation of stock fluctuation, that means over time, how much it fluctuates. Here we can say standard deviation of resource getting disrupted. Correlation among stock fluctuations. So if McDonald's goes up and down, what is the probability Bristol Myers Squibb also goes up and down? Here, if a camera goes up and down in terms of a camera quality degrades, what is the probability that another camera quality also degrades if they are very close to each other? If there is a network or a wireless channel being used for both these cameras, and if the wireless channel goes down, obviously these two cameras will not be able to send their data because the same channel is being used by these two cameras. So they are correlated. So correlations among resource disruptions. Expected return from a stock is expected utility from a resource. So that's how we are kind of finding parallels, and we'll apply the theories of portfolio theory for reliable system design. So again, this is how we formulate the problem. This is a paper under submission, a lot to unpack here. So I'll just go one by one. So the covariance and yeah,
Actually, time is up. So can you please short?
please wrap it up. Okay. So we'll not talk about this at all. We'll talk about maybe just quickly this result. Like here we show that a portfolio theoretic approach not only can give you better quality, it also gives you less standard deviation. So you see traditional approaches where you only deal with the expected utility and not the standard deviation, or not the like the fluctuations and the correlation. In portfolio theory, we're taking care of the correlation. So that's why the standard deviation, that means that the quality fluctuations is much higher in traditional approach, but the quality fluctuation with portfolio theory is much lower. So that's the big picture idea. So in conclusion, just-in-time edge environment are crucial for satisfying real-time requirement of most AI applications in examples or in use cases like emergency triage, disaster response. And there are many diverse metrics or diverging metrics, very difficult to align them. It's a non-trivial problem to solve. And novel solutions must be explored for system design challenges. So one solution doesn't work. So for each use case, you have to find new solutions. And because of the just-in-time edge environment, inherently there are some issues, there are some vulnerabilities which we have to deal with. And the need of the hour is to find reliable solutions instead of finding problems or solutions for each problem. So kind of different strategies. So for system design, have separate solutions. For reliability or for security, have one solution that kind of solves most of the problems. So that is kind of the essence of what we found in the last couple of years or maybe 3 years of work. So that's the point. Thank you so much for your time. Most of the publications can be found here, and there's my email address. So if you have any questions, just let me know and just send me an email and be more than happy to discuss. Thank you so much.
Yeah, thank you, Dr. Saptarshi, for your great and insightful presentation. And the floor is for the audience. We have a couple of minutes. If you have any question, you can ask. You can unmute yourself and please ask your question. Or you can send email also to Dr. Saptarshi. So you can unmute yourself and you can ask your question because we have few minutes time. Yeah, so there is a question in the chat box. Based on your research knowledge, what are the potential operational consequences of such attacks in collaborative IoT and edge environments due to hackers finding new loopholes to break the layers?
Yeah, I think these, especially I can talk about just in time because edge is much more like bigger umbrella. Because that goes somewhere else. We are just talking about just in time edge. Yeah, it's as I said, like it's highly vulnerable because it's loosely coupled. You just set up a system, you take like maybe half an hour to set the system up, make sure these connections are made. Sometimes it's internet based, sometimes like local network based. The devices sometimes are not compatible with each other. The drivers are all out of date. So, but the point is, this is an emergency, right? In most cases, you have to make it work. And so you get it work, right? Okay, you know that there are vulnerabilities, you get it work, that's how you run it. You know there are vulnerabilities. As I showed 3 examples, there are many vulnerabilities. I'm pretty sure there are papers coming out almost every day on different vulnerabilities of these kind of systems. But what we are arguing is for each vulnerability, finding out a problem and solution, it makes the system more like a not just in time edge system. If you want to put firewalls here, if you want to put guardrails there, you want to do like secure login, all these things, that will completely defeat the purpose of a just in time edge environment. The entire purpose is set up the system, get it working. You want to work it for next 2 hours or maybe next 2 days, but it's very short term. So let's not put all these barriers. What you do is design the system such a way, like manage the system such a way that most of these problems that exist, the effects are not felt that much. And that is what we are trying to do through this portfolio theoretic approach, that we'll design the system, we'll choose cameras, or we'll choose in wireless channels, or we will choose where to send the data, where to do the partition, right? In a way that is by default a little robust than if you do it in a different way. That's the point we are trying to get. And this is a very unique approach than any other like system design or system reliability problem. And that's why we find this a very challenging and very like interesting problem to solve. Yeah.
Yeah, one more question from audience.
Sure.
One more question. . Okay, if there is no more question, then I have one question. So
Sure.
can you extend this work, especially edge computing concept in other domain, including healthcare, especially
Yeah,
we are
yeah,
very medical college.
exactly. So, like in healthcare, like again, this work is about just-in-time edge. So, just-in-time edge for say medical triage is like ideal, right? If you have a disaster, and again, if we are talking about disaster from a fire department point of view, you can talk about disaster in like healthcare point of view. You want to do a medical triage, figure out which area you need more like rapid response, or which patient needs immediate care than some other things, right? For that, what you need to, again, you cannot rely on a human being to do all these things. You have to rely on machine, you have to rely on AI/ML. And again, what you need is a ad hoc environment where you can run these AI/ML applications which can do this thing for you. But then while you run something like this, there will be vulnerabilities, there will be issues, there will be disruptions, and these things can be applicable. Beyond that, I think this, so what we are trying to get, so right now we are talking about only disaster, like just in time, but this is kind of a, it's an example of a big picture idea. The big picture idea is managing resources which are loosely coupled, right? So that can happen in different places. It doesn't have to be only just in time edge. Wherever you have a system where the components are loosely coupled, I think you can apply these principles. So what we are trying to come up with is principles of system management which can be applied anywhere. And I think if you have a loosely coupled system, kind of for some problems where you and I are working on, right, like elder care facility, maybe healthcare, in that respect, have a loosely coupled system, why can't we apply some of the principles that we have here and over there to see how does the system react and how does the system make it more reliable? So yeah, it can be definitely extended to healthcare. Yes. Long story
Great.
short.
Yeah, great. Thank you. Thank you for your presentation. And I think here I can stop. And once again, I would like to thank you, extend my heartfelt thank you for your nice presentation. It was insightful and many things we learned from your presentation, especially edge cloud computing concept, edge cloud interplay concept in emergency situation like fire, even in healthcare also. I think for elderly care people, there also we can apply this type of concept. Also, the optimization technique for accuracy, then latency, as well as energy consumption. So especially when it is dealing with the IoT device, so there we need some optimization technique, and also the attacks related to AI machine learning model, data poisoning. So I think many things, many topics you covered. So again, once again, I thank you for your great presentation. And also I would like to thank all the audience. I think from Vanderbilt University, from Fisk University, they joined, they spent their time, and hope you enjoyed this talk. And in this seminar series, we have our next talk. Our next presenter will be Professor Soroja Mohanty from University of North Texas, and it will, I think the schedule is on April 16 at the same time, 12 p.m. 16, and he will present his talk on secure cyber physical system by design. So that will be another great talk. And again, once again, thank you for your time, and looking forward to meet you again in the next month.
Thank you so much for the opportunity. Thank you. Bye bye. You guys have a great day. Thanks.
Thank you.